Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thanks so much for joining me for another video in our Rust programming tutorial series. Now, in our last video, we studied how to use the date and time types in Rust. We actually had to reach out into the Chrono Crate in order to work with actual dates and times because some of that functionality just isn't available in the Rust standard library. Now, I'm going to continue focusing on the standard library because there's honestly still a lot more concepts that we still haven't covered in this tutorial series. I don't want to belabor the point of studying the fundamentals of Rust, but it really does behoove you to study the fundamentals so that once you start developing more advanced applications, it makes more sense how the different pieces fit together, how things like borrowing variables work, how mutable variables work, how closures work, and all those other kinds of concepts. So what we're going to be focusing on in this particular video is the introductory basics of the threading model in Rust. Now, for starters, I just wanted to start with the basics here. So I put together a simple diagram here for us to use to kind of mentally visualize what it is that we're dealing with here. Now, when you do a cargo run operation here, typically you are kicking off a single process here, right? And that's your Rust process that gets compiled and executed on the operating system. But that process actually gets broken down into individual threads. And typically, you're just going to have a single main thread where you run your code unless you explicitly create additional threads or you call out to some library that creates additional threads on your behalf without having to manually manage them in your part of the code. Also, on the far left here, we have our CPU sockets, right? So some systems, maybe a desktop workstation or a laptop, will quite commonly just have a single CPU socket. But these days, pretty much every CPU out there is going to have multiple cores, right? So in this particular case, we have an example of a two-socket system. So this would probably be a server system that's got more than one physical socket to install a CPU into the motherboard. And then we have sockets numbered 0 and 1 here. And then if we break down the CPU cores in each of those sockets, we have, item 0 through 7 here for representing the individual CPU cores. Now, even beyond the individual cores within a CPU package or socket, we also have what's known as hyperthreading. This was originally a concept that was created by Intel some years ago, where the CPU hardware is able to represent these virtual cores, so to speak. So from the operating system's perspective, it looks like it has maybe 16 cores, whereas there's only actually physically 8 CPU cores in the system. And under certain types of workloads, that can improve the efficiency of the CPU package. But regardless of whether you're using hyperthreading or not, or regardless of how many CPU sockets you have, the idea here is that we have our threads in our application, again, typically a main thread, and that thread, let's say that this top little crustacean here is a main thread, and then we have maybe 2 additional worker threads that we create right here. This main thread will ultimately get scheduled onto one of the CPU cores in the system. As a software developer, we don't necessarily care which CPU core specifically that thread gets scheduled on. That's more of kind of a systems architecture type of thing or systems management type of operation that you might concern yourself with to kind of optimize system resource utilization. But again, from a Rust development perspective, we don't necessarily want to schedule a thread on a specific CPU core. Instead, we just let the operating system handle that for us. And typically, when you kick off a Linux process, or even a Windows process for that matter, your operating system is typically going to allow that process to be scheduled on any of the CPU cores in the system. Or more correctly, I should say that any of the threads that are part of that process can ultimately get scheduled on any of these CPU cores, right? There are ways for you to actually limit which CPU cores can participate on threads in a given process. So in Linux, there's a utility called nice, and it basically allows you to allocate certain CPU cores, like maybe 0, 3, 5, and 7, if we want to take all the odd numbers like 1 through 7 here. I don't know why I said 0 because that's an even number. But yeah, maybe 1, 3, 5, and 7 here. And we could allow our threads for our Rust process to only run on those CPU cores. But again, that's not something we necessarily concern ourselves with as developers. But we just want to understand that our individual threads in our Rust program that we spawn, whether it's the main thread or additional worker threads, get scheduled onto certain cores. And that decision is ultimately made by the operating system kernel. So this is kind of what we're dealing with here. We want to start with our main process here, which we've already been doing inherently, but we also want to be able to spawn these additional worker threads inside of our Rust code, and that's what we're going to be taking a look at here. So in order to accomplish this, what we can do is reach into the standard library again, and there's a module. There's a whole bunch of child modules exported by the standard crate in Rust. And if we take a look a little bit further down here, you'll see that there's a module called thread. And this is not a super complicated module here. There's only a handful of data structures here that we deal with and functions down here. In fact, in one of my earlier videos, it might have been the last one, I actually used this thread sleep function here to just sleep a certain amount of time so that we can kind of emulate some work being done. But if we actually want to do some real work and actually exercise the CPU and put its power to use, then we can create these additional threads. So right here, we've got a thread struct in the thread module, and we also have a join handle here, which gets returned when we instantiate a new thread. Now, if we drill into the documentation for the thread struct in the thread module, then we will see several different methods that are available here. But in particular, we're actually looking for this function here called spawn. And this is something that we can call directly on the thread type. Actually, it's a function of the thread module. Sorry for that correction here. It's a function of the thread module that returns a new thread by giving us this join handle here. So in the input arguments for this spawn function right here, we're actually going to be passing in a closure. So if you don't understand what closures or anonymous functions are, then go back to my earlier video in our playlist on Rust programming, and that'll describe what a closure is. So essentially, the spawn function is just going to take a closure as input. It'll spin up a new thread, and it'll return this join handle that we can use to keep track of the status of that new thread that's been created. So we're going to go ahead and just call this spawn function here. We'll take a look at how to create a closure that does some, kind of random fake work just to kind of exercise the CPU. And then we'll take a look at the join handle here to see what we can do with this. Now, once we have the instance of the join handle that gets returned from the spawn function, there's a couple of different methods here. There's not a whole ton that we can do with it, but there's is finished. So this will just return a Boolean value indicating if the thread has completed its work or not. There's also the join function right here. And what this will do is it'll wait for the thread to finish, and then it will return a result object so that we can retrieve any results out of the thread. Or if an error occurs inside of the thread, like a panic, then we can actually capture that panic and see what the problem was. And we've also got a reference to the thread itself. So we've got this pointer to the thread struct itself, which then gives us access to things like its ID, name, and so on and so forth. There's a whole bunch of other functions available on the thread type here as well, but I'll let you explore those on your own. All right, so what we're going to do is jump over into our code editor here. I've got VS Code connected to my remote Linux virtual machine here. Also, you'll want to make sure that you have enough system resources. Back before I started recording this video, I actually realized that this Linux system, if I run btop here, only had a single CPU core allocated. So I made sure that I allocated 3 CPU cores. I've got an i5-8400, which is an older Intel architecture. I think it's the Coffee Lake architecture. And this particular CPU model has 6 CPU cores, not hyperthreads, but 6 actual cores. So I'm allocating 3 of those cores to the virtual machine. And I also bumped up my memory just a little bit to make sure that I've got plenty of memory, because I had actually been using the defaults in LXD, which is 1 gigabyte. So I gave it about 3 gigabytes, which came out to about 2.6. And so I've got plenty of free RAM here because we're only using about 660 megs of it right now. So we're going to be using BTOP here to kind of keep an eye on the status of our individual CPU cores on this VM. And for starters, we're actually going to see how doing some work on the main thread in Rust is only going to consume a single core because it's not multi-threaded. And a thread can only be scheduled by the operating system on an individual core. It can't be broken apart across multiple cores. So what we're going to do is go into our sample application here, and we are going to create a new module here. Let's just call this mythreads.rs. And what we're going to do in mythreads.rs is define a public function here. We'll say test threads, and we'll put our open and close curly braces. And then over in our main file here, we want to declare that module externally. So pub mod mythreads. And then we'll be able to call test threads from our main function here. So let's head down to the bottom. We'll comment out test chrono, and then we'll do my threads test threads, and we'll call that function. So right now it's not doing anything, but inside the body here, we're going to go ahead and fake some work. So for starters, I said we're going to exercise the main thread and see how the work is limited or scoped to only a single CPU core. So really quickly, let's just create a variable as x, and we'll make it equal to 0 as an unsigned 128-bit integer. And then what we're going to do is just create a for loop here that says for I in a range of 1 to, let's say, 500 million here. We're just going to do x plus equals I. So we're basically going to take the number 1 and add it to x. Of course, we need to make x mutable as well because we're changing the value or mutating the value of the x variable. So we're just going to add 1 to x, then 2 to x, 3 to x, 4 to x, all the way up to 500 million. And that's why we allocate a relatively large address space like 128 bits, just to make sure that we've got enough capacity for x when we add all these numbers together. And then what I'll do is maybe, well, I'm not going to do a print line statement here because all we want to do is just do the mathematical operation. All right, so it's still warning us here because we never actually read the value of x. So, we could do a print line at the end and just spit out the value of x, but I really don't care about that. So we're just going to ignore that warning. All right, so inside of VS Code here, let's go ahead and split our window pane right down here. And I'm going to bump down the font size just a little bit so that we can provide enough capacity for BTOP to run here. And then I'll scooch this little window over a little bit just to give it enough space for BTOP. And let's make it a little bit wider here. Or there it is. All right, hopefully, there we go. So now I'm just going to do a cargo run. And we should see that one of our CPU cores here, so it looks like the operating system scheduled our main thread on core number 1, and that's where the operation is executing. So that ran pretty quickly right here, so it already exited right here, but we could always bump that number up to something higher, maybe just add some more zeros to it right there, do a cargo run again. And this time, the next time we run it, it looks like the OS allocated that thread to core number 0. So every single time that we spin up our process and that process creates its main thread, the operating system has the opportunity to specify which of these CPU cores it wants that thread to run on. Now, let's say that we wanted our Rust program here to do some additional work beyond just what the main thread is doing. So I'll do a Control-C to cancel that process right now. Then I'll do Control-tilde here to minimize my terminal. And let's go back to our code here and spawn a thread. So I'll do pub fn spawn thread. And inside of this function, I'll just call this, well, I guess we could just call that directly from our main here. So let's do comment and mythreads spawn thread this time. So what we're going to do in spawn thread is actually create a new thread using the spawn function. So typically what we need to do is say use std thread, and then we want spawn here. So that'll import the spawn function from the standard library, and then we should be able to just call spawn right down here without having to use the fully qualified path to system thread, which is another syntactical option that you have. But we can just call it like it's a native function because it's been imported into our module. And then the input argument here is going to be the closure that we want to execute inside of this function. And remember from the video on closures, a closure is an anonymous function, and we can even assign that function to a variable. So just to keep our code a little bit clean here, what I typically like to do is specify a variable, something like myFN, or maybe to be a little bit more explicit, thread fn. And then we're going to assign the result of a new closure. So we'll just do a couple of type characters here to denote our input arguments. We don't need to accept any input arguments here for our thread. And then what we'll do is just take this code right here that does some mathematical work inside of our thread, and we'll make that the body of our closure function here. So now we have a variable called threadFN that contains a closure, and all we want to do is pass threadFN into the spawn function, and that will satisfy its input arguments here because spawn only takes that closure as input. Now, just to satisfy this little warning up here, I'm going to go ahead and just say print line at the very end, and we'll print out the value of x. All right, and that takes that warning away. And then for the spawn function here, remember that we talked about in the documentation how the spawn function returns this join handle so that we can keep track of the progress of the thread that we kicked off. So what we'll do is assign the handle to a variable here, and the Rust compiler will infer the data type, which is a join handle, returning a unit type, which is basically a placeholder for none or a null value. And now we have this handle, and what can we do with it? Well, before we get into that, let's try to run this program and see what happens here. So we're going to go ahead and do a cargo run again here. And let's see. So actually what's happening here, this is what I intended. I don't know why I was confused by that. But what's happening here is that our program starts and it immediately exits. And your first thought might be, okay, well, if I go to main rs, did I even call that function? And yes, I did. So what I'll do is just print a debug statement here. So we'll say print line, starting new worker thread. And that way we can actually see that it is starting. So sure enough, down there it says starting new worker thread. And then after the process here, we'll say worker thread completed, save that, and rerun this. And now it says starting new worker thread and worker thread completed. But remember that we copied this code right up here from our test threads where we saw it was actually taking quite a bit of time to do some work. And the other thing that you'll notice is that we never get this print line containing the value of x. And I'll just change this to say value of x is colon, and then pass in x there. And again, a shout out to one of my viewers, I think it's Meow Squeak, who a couple videos ago suggested to me that you can use this syntax right here to directly pass in a variable into a format string so that we don't have to pass it in as an argument like this. So thanks to Meow Squeak for that again. And so what's happening basically here is that because our main thread is kicking off this secondary worker thread, the control is being directly returned back to our main thread. So even though we kicked off this background thread, the main thread is not going to wait around for that worker thread to finish. So what we can do in order to tell the main thread to block until that thread is finished is to use the join function. Remember, if we take a look at the join function on the join handle struct here, the join function is going to wait for the associated thread to finish. This will cause the main thread to block execution of any other code until that worker process is finished. So what we'll do is say handle.join, and that will cause it to wait for the worker to finish. And we are going to get a warning here saying that there's a result coming back from join. We don't have to capture that if we don't want to, but typically if your thread is going to return some data, or if you expect that it's going to panic or something like that, you can capture that result value and inspect it to see what the result actually was. But for now, we'll just call join. And this time, if we try to run our program again right here. Let's make this a little bit bigger. We'll do cargo run. So now you can see that the main thread is blocking right down here, and it's waiting until that worker thread has finished. So that worker thread has now been scheduled on core number 0 here, and it's consuming the entire CPU core. Now, let's say that we wanted to use 2 CPU cores, right? So this is where multi-threading really comes in handy. We can actually improve the efficiency of our resource consumption on our infrastructure by creating these additional threads and letting the operating system schedule those threads onto the other CPU cores in our system rather than just letting them sit idle. So what we'll do is actually spin up a second thread here. So I can literally just reuse this closure right here that has the worker code inside of it. And then let's just do a Control C there to cancel execution. And then we will spin up another instance. So on line number 19 here, where we call spawn and return a handle, I'm just going to copy that down, do Alt-Shift down arrow, or I think on Linux it's actually Control-Shift-Alt down arrow. And then we'll say let handle 2 equal spawn again. So all we have to do is assign a new variable with a different reference to a join handler. So now we have 2, not just 1. And because both of these threads are going to be running the same complex code here, and it's going to take quite a while to run, I don't necessarily need to wait on all of them, but I could duplicate this line here and just say, all right, first I want to wait for thread number 1 to finish, and then after it's finished, I want to wait for thread number 2 to finish. Now, this can be problematic because if thread number 2 finishes very early, then the first thread here is still going to be waiting. And maybe that's a good thing in your particular case. But if you don't want the main thread to like totally block, then what you can actually do is another technique by checking the isFinished attribute or method and seeing if the result is true or false. And then you can allow the main thread to continue doing some work and then just periodically check in with each of these thread join handles to see if they're finished or not. So then we can have our main thread doing some work, periodically checking in with the worker threads, but the worker threads can also be off doing their own work on their own separate CPU cores as well. But for the time being, we're just going to say wait on thread 1 and then wait on thread 2. All right, so back over here in our terminal, I don't know why this keeps getting resized down. We're just going to do another cargo run right here. And now we should see 2 CPU cores being completely filled. So core 0 and core 2 are currently at 100%, and we still have some capacity right here on core number 1 to do other types of work. So as you can see, the operating system is taking our 2 threads that we spawned here, it's scheduling them onto separate CPUs, and everything looks great. So let's Control C that. We'll just cancel that process. And then what I want to show you now is how we can actually have the main function do some work in addition to the worker threads. So what we're going to do is after we instantiate these 2 threads right here on lines number 19 and 20, we're actually going to tell the main thread that we want it to call this test threads function here so that the main thread also can do some work while the background worker processes are executing. So after lines number 19 and 20, before we wait for those threads to finish, we're actually going to give the main thread here some work to do by calling test threads. And because we are not oops, I'm trying to define a function there, not call it. So this is going to tell the main thread, do this work, while these 2 guys over here are doing their own separate work. And then after the main thread is finished, then it'll go ahead and wait if those workers are still doing extra work. It'll go ahead and wait on them just for safety so that they don't get canceled prematurely. But this way we can kind of take advantage of all the threads that are running in our process here. All right, and because we have 3 cores in this system here, we should see that all 3 cores get filled up with some work. And as you can see, when we run this, our main thread is running on 1 core, and then our 2 other worker threads are running on 2 other cores. So we are making the full use of the resources available to this particular virtual machine. So if you're deploying applications in the cloud and you want to make sure that you're not wasting CPU capacity on your expensive virtual private servers, then make sure that you use Rust threads in order to accomplish that objective. Now, I did want to show you the isFinished method on these join handles really quick as well. So one alternative that we have to just waiting arbitrarily on these, is to create a loop. And so inside of this loop here, what we're going to do is basically check to see if handle 1 and handle 2 are finished. And if they're not, then we're just going to continue to loop. Otherwise, we'll break out of the loop. And what I'm going to do is just comment out test threads right here. And maybe what we'll do is actually modify it just to do a lot shorter work. So it's still going to do some work, but it'll be shorter units of work each time. And so we'll just say print line, main thread finished a little bit of work. Let's go check on the worker threads. All right, so we'll save that. And I'll also turn this into red text by using a ANSI escape code here. I know this is probably a little bit confusing, and we'll probably do a video on this at some point, but we're just going to make this a different color by using this special ANSI escape code that creates a custom RGB color here. And then at the very end here, I'm going to reset that formatting by doing /x1b and then 0m. All right, so we're going to see the main thread doing some work, but then inside of this loop here, we need to call test threads. And then we're going to say if handle dot is finished and handle 2 dot is finished, then we're going to say print line, all the workers are done, comma, let's get out of here. And so this will cause our entire process to terminate by breaking out of this loop. So the main function isn't going to do its little units of work right here, because now that our worker threads are done doing their bulk of the work, the main thread just says, all right, we're done. Thanks for doing your work. Now we're going to exit. We're all going to go home. All right, so let's give this a try once again. And we'll say cargo run. And what you see right here is in this blue text, the main thread is doing a bunch of work and it's waiting for each of those threads to finish. And those threads are going to take quite a while, right? So let's actually just do a Control C, and then we'll bump the value down here back to, let's say, how about we do maybe 50 million? That should be plenty of work. So if we do cargo run, you can see that the main thread is able to iterate on its work. And then finally, at the end, we have our worker threads that complete right down here. So this is a pretty cool way of doing multi-threading here. So feel free to play around with the spawn function here, and then take these join handles and use those to kind of check the status of those other worker threads. And you can always kind of determine how many CPU cores are in the system. And then you could dynamically spin up a number of threads based on how many cores are available to the system, so that you can kind of maximize the use of the system without necessarily stepping on the other thread's toes. So anyway, that's what I wanted to cover in this video, is just kind of an introduction to threading our Rust programs. It's pretty easy to do. And before we end here, please go out to my YouTube channel, youtube.com/Trevor Sullivan. Please subscribe to the channel and hit the bell icon as well, so you can get the notifications about new videos. And make sure that you're following the Rust programming tutorial playlist here, because this is where I am posting all of the new videos on Rust software development. Thanks for watching, and we'll see you in the next video. Take care.